There are roughly 1.5 billion combustion vehicles on the road today. Electrifying that entire global legacy fleet overnight, or even over a few decades, presents a massive logistical bottleneck. So engineers are testing a parallel solution. On the right is standard fossil fuel. On the left is a synthetic liquid fuel, chemically identical to today's gasoline, but manufactured without crude oil. The process works on a carbon-neutral loop. If the carbon dioxide used to make the fuel is captured directly from the air or from a biogenic source, combusting it in an engine simply returns that exact same amount of carbon back into the atmosphere. Because this synthetic fluid is what we call a drop-in fuel, you can use the existing fleet, existing pipeline networks, and current gas stations without a single modification to the engine hardware. Synthetic gasoline offers a perfect mechanical solution for the internal combustion engine. However, the exact physical chemistry that makes it all work also makes it extraordinarily energy expensive to produce. The production chain starts with electricity, a lot of it. This first stage uses renewable power, like wind, to split water in an electrolyzer, creating a feedstock of green hydrogen. This is the most energy-intensive part of the entire process. It consumes between 45 and 70 kilowatt-hours of electricity to yield a single kilogram of hydrogen. Next, you need carbon dioxide. To keep the climate math balanced, this gas must be captured directly from the air or piped from a concentrated biogenic stream. Finally, the hydrogen and carbon dioxide are combined through fuel synthesis. In many current designs, this involves first creating e-methanol and then running it through a specific methanol-to-gasoline reactor process to build the final hydrocarbon. This is happening right now at the Haru Oni pilot plant in Punta Arenas, Chile, where the constant Patagonian winds provide the abundant electricity required to run the facility. The facility successfully produces synthetic, low-sulfur gasoline today. But scaling this molecule-by-molecule construction from pilot volumes to a mass-market supply introduces severe constraints. The hardest fact about e-fuels is thermodynamic. Every single conversion step in the e-fuel process loses a percentage of the original energy. This chart shows the energy cascade. Starting with 100% renewable electricity, you take a heavy penalty during electrolysis, another during carbon capture, a third during fuel synthesis, and a final massive cut combusting the liquid inside an engine. By the time the wheels actually turn, the well-to-wheel efficiency of a car running on liquid e-fuel is roughly 15%, and often lower. For comparison, look at a battery electric vehicle. Because it skips the chemical synthesis and combustion stages entirely, it delivers roughly 70% of the original electricity straight to the road. To put that in practical terms, driving the exact same distance in an e-fuel car requires 4 to 5 times more renewable electricity than driving an electric car. That intense energy requirement dictates the economics. The capital and energy put into each liter keeps early-stage synthetic gasoline vastly more expensive than fossil fuels. Relying on scarce renewable electricity to manufacture fuel for everyday passenger commutes defies basic efficiency logic when direct electrification is available. Despite the physics, e-fuels remain heavily debated, driven largely by regulatory shifts like the European Union's evolving 2035 car emissions rules. Policymakers might carve out legal room for carbon-neutral fuels, but the sheer thermodynamic advantage of batteries means the bulk of light vehicle decarbonization will run on direct electrification. Where synthetic fuels make genuine engineering sense is in heavy transport. In aviation, batteries are simply too heavy to replace the high energy density of a liquid fuel. The same logic applies to global maritime shipping and to legacy classic vehicles where no electric alternative physically exists. Synthetic gasoline will likely persist as a specialized premium tool for the narrow range of heavy industries that cannot be electrified directly. The mechanical side of the combustion engine is essentially a solved problem. The real engineering challenge now shifts to the generation and efficient allocation of clean energy. To explore detailed thermodynamic scaling models and review the real-world data behind sustainable fuel infrastructure, check out the resources on our platform.